Hello, my name is Clayton Cook, and I will be presenting for the Saginaw Valley State University NASA Lunabotics event. The initial thing we start out with is the significance of the systems engineering method. This method is used by NASA to ensure products are developed efficiently by delegating and assigning tasks. We use this to avoid issues of conflict and redundant task assignments. However, this has ended up failing once we moved into a more cross-departmental project just due to miscommunication. Design optimization criteria. Our main focus was to minimize the weight and implement full autonomy. Our first goal was maximum weight of 30 kilograms, and our second goal was to complete at least 2 fully autonomous mining cycles. These criteria were kept in mind during the major reviews of the project. 3 major types of review according to the NASA Systems Engineering Guidelines include System Requirements Review, Preliminary Design Review, and Critical Design Review. To fit our dynamics, these reviews were modified to System Requirements Review, cross-department meetings to rules and identify optimization criteria, Preliminary Design Review, internal department meetings, electrical, mechanical, and programming, where designs were proposed and reviewed by department advisors. Critical Design Review, each department presented their findings to the entire team to be approved. The specific departmental team would then finalize the design choices. Here is an overview of our project timeline, and then another overview of our budget. The electrical system consisted of power distribution, controllers, and communication systems. Our system communicated with the onboard computer and received commands. Our programming system developed to know where the rover is to avoid obstacles in between each dig, called SLAM Rock, simultaneous localization and mapping with rock detection. To do so, a mapping program was developed to use images on the onboard camera and matrix calculus to map the environment. Here's an overview of our system hierarchy. Here is our technical performance measurements. For our mechanical system, we had a dimension of 1.1 meter by 0.6 meter by 0.6 meter and a mass less than 30 kilograms, and it should be able to move predictably on a simulated surface of the moon. As for the electrical system, a 4-wheel independent design offered a good balance between the 3 major design criteria: energy density of the motors, small footprint, and high ratio. The electrical control system was programmed using C++. And for the navigation system, we used the SLAM and object detection together as a whole navigation system unit. We used SSD MobileNet v2 to train the object detection system to avoid obstacles. For our reliability, aluminum square tubing was used to optimize the strength and minimize the weight. A conveyor belt was used to allow the robot to not require a smooth deposit surface. A direct drive system eliminated the failure points introduced by tracks, allowing for easier turning and control for the electrical systems. Due to schedule constraints, the team opted out for testing in a simulated environment instead of testing on flat ground. Fail-safes were implemented with the drivetrain so the robot could still operate if 2 wheels lost traction. To increase reliability of the SLAM algorithm, ROS subscriptions and parameter tuning was used to better fit the project's needs. The system requirements verification. For the mechanical team, it does not meet the initial mass requirements due to the size needed for the arm to reach the regolith layer. The robot does fit within the size limit and has the capacity to reach the required depth. For the electrical team, motor testing had ideal current draw and torque, and the electrical system was selected to stay within the weight limit while also retaining the power requirements. As part of our SLAM algorithm for the programming team, it was seamlessly integrated with ROS, and the streams were validated by creating a simulation test. Additionally, the path following algorithm used real-world tests to increase the resolution of the path. For the object detection, it successfully was able to detect objects. It was able to draw bounding boxes around 1 or more rocks, and it was tested with real-world scenario, yielding slightly less scores, but still ample success. And finally, for the USB serialization and network sockets, an ROS Arduino library was used for serialization.